We'll look into the analysis of data, starting with the measures of position. They are also called as quantiles. So these are the values which are at a particular position of the values of x. So we majorly use the four categories of measures here, but you could define any such measures and you could compute them. So we have median, then quartiles, deciles, and percentiles. What are we going to here is, so we have a distribution, that is we have a variable. So it is taking several values, its values. Now you want to pick the value of x, which are, which are of your interest and which are at particular position. Say you need the value of x in 25th position or in the 50th position, or you want to obtain the value of x which is exactly, covering first 50% of the data, or the value of x where first 10% of the data is collected. What is the cutoff value of your data at the 90%? So if you are interested in picking the values of that particular variable, then we say we are interested in obtaining the quantile values. Now the very first common quantile which we use is called as median, and it is also called as an average because it is the central value of the data. So what we do here in case of median is we are obtaining that value of x which is dividing the distribution into two equal parts. So you're picking the middlemost value in the data. And this property of middlemost is that it is covering 50% of observation on either side of that particular value. And this median is indicated by n. And you could call this as a positional average also, because it is also a measure of central tendency, which we'll be discussing again after completing this. And then it is also a measure of quantile. Now there are various formulas available to obtain the value of median, but simply if you look into the definition which says median is the middlemost value, we mean you have to have the logical arrangement of your data. So either in the increasing or decreasing order, preferably increasing order. So because when we talk about the middlemost value, whether you're looking in an increasing arrangement or a decreasing arrangement, the middle number remains the same. So arrange the data in the increasing order, pick the middle number. That middle number is said to be the median. Now, in the field of statistics, we describe the data, qualitative data, into three particular forms, which are raw data, discrete data, and continuous data. Now, these discrete and continuous come under the frequency distribution concept. So, if you have data in large number, where your n is large, you try to condense the volume by presenting them in a form of frequency distribution. On the other hand, if you have just the values of x, where n is very low, like you hardly have collected 10, 15, or say 8, 5 observations, then for those set of small data, representation in the form of frequency distribution is not required. So we take it as the individual values and we could obtain the data, I mean the measures. Now this now as the type of the distribution changes from raw to discrete and continuous frequencies, the method of obtaining these values, these measures also changes. Now when we have just the raw data in the sense the data collected in an unordered form, or raw is nothing but the original or the unordered data. Say for example, you have obtained or observed age of say 6 particular patients who have visited, and you have arranged them in an order. Say this is the increasing order. Then you pick the middlemost value. Now here we indicate the number of observation when it comes to raw data by small n, and here we have 6 observations. Now I want to pick the value of x such that it covers the first 50% of the observations. Now, since n is equal to 6, the 50% of observations comes just immediately after the number n is equal to 3 or the position 3. So, if you assign the position, we are talking about the number which is after 3. But if you look into or if you pick 40, that is not dividing the distribution exactly in the ratio 50 and 50. So I have to pick the number such that it is dividing the ratio, or it should be the middlemost number. But when we have n is equal to an even number, we pick two middle numbers. There will be two middle numbers. We take the average of those two values and we compute that as median. And average of 30 and 40 is 35. So in this case, I say the median of the distribution is equal to 35. Now, often in the cases where there are very low values in the data, very high values in the data, the arithmetic mean gets fluctuated because of the presence of those extreme values. In those cases, we say median is the preferable data. On the other hand, if you have the data which is obtained in the ordinal scale where the logical arrangement is possible, even in that case, the suitable measure will be median compared to arithmetic mean. Now, the computation of median is just very easy. It is just by the keen observation. Just arrange the data in the logical order. If you have odd number of observations, you can easily pick the middle number. If you have even number of observations, obtain the average of those two middle numbers. So this is the middlemost value or the value of x such that it is covering 50% of observations on its either side. Now the next set of values are such that they divide the distribution into four equal parts. So the values of variable which divide the distribution into four equal parts, which divide distribution into four equal parts. If I want to divide a distribution into four equal parts, let's say you have a distribution like this, then you will obtain the middlemost value first. So that is dividing the distribution into two equal parts. And of the every half of the distribution, again you divide that into two cases, you will get three measures. And these three values are called as quartiles, and they are producing four equal parts in the distribution. So first quartile is indicated by Q1 and it is also called as lower quartile. Second quartile is indicated by Q2, it is called as the middle quartile. And the third one is called as Q3, also indicated by Q3, also called as upper quartile. If you look into the property of this Q2, it is covering 50% on either side. So it is sharing the same numerical value as that of the median. Now coming to the property of Q1, Q1 is that value of x such that it is covering 25% of the observation towards its left and remaining 75% observation on its right. Similarly, you can produce various such quartiles. So in case of deciles, we try to divide the distribution into 10 equal parts. So if I want to divide the distribution into 10 equal parts, so 9 cuts are sufficient and those 9 values are said to be the values of decile, and we observe them as D1, D2, etc. up to D9, and D5 again shares the same numerical value as that of this. And then percentiles talk about those 99 values which of x which divide the distribution into 100 equal parts. Now these measures have their own use in the field of statistics, and they are used in deciding or chopping off or cutting the distributions in order to make them free from the available extreme values. And some of the measures like say quartiles especially, it is used in various other measures or measures of variation, measures of skewness like quartile deviation, interquartile range, skewness, etc. So we'll discuss them in detail. Now we'll just look into the computation of median for all the cases, and just the knowledge of the other measures are sufficient. We'll not look into the calculation part of these cases. Now coming to the other application. So as said, your data will have extreme value. So whenever you are presenting, collecting some data, maybe because of some human error or because of some chance, you could observe very low value in the data as well as very high value in the data. So if you have collected some numbers like this, so you may have certain values which may seem that they do not seem to fit into that particular data set. So those are said to be the extreme values. Maybe instead of recording the value as 10, the person might have recorded as 100, or instead of capturing the value as 0, he might have taken it as 0.01. So they logically doesn't seem to be present in that particular set. So if I involve them, then it affects some of the measures. So before doing the analysis, I have to see whether it truly representing the value of that particular variable, or is it by chance that is recorded. So in that case, if it is the true value, now I have to decide whether to include that point in the data, or should I omit them. Now, in order to omit the distributions, or in order to chop off the values, so when we arrange the data in the increasing or decreasing order, always the extreme values will be either in the left part or in the right part. So if I could divide the distribution into various segments, and if I chop out, say, first 10% or the last 10%, or first 2%, last 2%, then I need the cutoff value which is covering the 90% of the observation, or which is covering the 98% of the observations. So in that case, I will look into the computation of values like quartiles, deciles, and percentiles. Now, based on your objective, you could obtain the points. So some also use what called as octales, which divide the distribution into 8 equal parts. You could come up with the measures which divide the distribution into 3 equal parts, which divide the distribution into n such equal parts. I will talk about this measure of median in detail when we talk about the measure of central tendency. So this is about quantiles. Now, one of the important part of this quantile is that you can also use this quantiles in uh, checking whether the data follows normal distribution or not. Now, the collection of the data or using the method of histogram requires large number of data values so that you can obtain a frequency distribution, and then from the frequency distribution you can construct the histogram. But when you have very small data set, and if you want to observe whether the data follows normal distribution, in that case one of the easiest method is to fit the distribution. That is, we try to obtain the quantiles for the collected sample values of x, and also we try to obtain the quantiles of the population which are already known, and in this case the population stands for normal distribution. Say we are assuming that height of soldiers always follow normal distribution. So there is a law or a probability distribution called as normal distribution. So as said in the last class, if I make certain assumptions in the theoretical part of the statistics, that leads to much easier calculations, and it leads to various certain decision making which becomes very simple. So in order to achieve that, we try to assume certain things, and one such case is every variable follows normal distribution. So to check that, you have to select some observations randomly. So select some soldiers randomly, measure their height. If I'm recording in centimeters, so I could have values like say 178, 171.5, 165, and so on. So I could select some, say n is equal to 10 or 12 such observations. And now what I can do is I can compute the quantile. So you fix the type of the quantile, whether you want to look into the deciles or quartiles or percentiles. And usually when it comes to a quantile plot, we look into the percentiles. So we compute the percentiles for the selected sample value. So this is my sample value because of all the soldiers of that particular country or battalion. I'm selecting only 12 random cases. So the set of all soldiers, that is my population, the totality of all the soldiers, that is my population. I'm assuming all the heights of such as a n soldiers are assume to follow normal distribution. In order to check that assumption, I'm selecting certain number of observations. Now what I do is I try to compute the percentiles for these values, and when I say the distribution is normal, the normal distribution percentiles are readily available. So we take the sample quantiles on x-axis and the population quantiles on y-axis, and we try to map them. And if at all a data really follows normal distribution, the plot becomes a perfect straight line. For a distribution which is very much closer to normal, the points may come around and fluctuate closer to the straight line. So usually we observe a curved line or a straight line along the points. The behavior of the points will be, it will be around the straight line. In that case, we say the sample values, whatever we have selected, or we could say that particular variable follows what called as normal distribution. So in this case also, only the knowledge regarding what are quantiles, what are the different types of quantiles, what is the application of quantiles, and what is a quantile plot, how it is constructed, and how it is used in deciding whether the variable is normally distributed or not. So only that knowledge is sufficient. So you could have a question on what is histogram, what is quantile plot, what are the applications. So only the theory part is sufficient here. Now, at times, or could say, one of the major disadvantage of this measure of position is that you are picking only specific values of x, and you are leaving out the information given by the remaining set of observations. Say if you have say 10 observations, and if you pick the value of median, you observe that median is not at all a value taken by x, because it is the value in between fifth and sixth. And if you are picking only that number as median, you are leaving the entire set of observations. So your measure is solely not based on all observations. Every observation, every data point, every sample point has some characteristic. It has a hidden characteristic of population, or it is showing certain behavior exhibited by the population. So we have to capture all those information given by each and every x values, so that the characteristics of population or the generalization of the results could be easily done. So the major, in order to avoid that, we try to look into the measures which are based on all the values of x, and such measures, some of the measures which are based on all the values of x, are called as measures of central tendency. When you look into any data which is randomly collected, you will observe that most of the points, the data points, cluster around a particular value. So whether it is age, height, or weight, you can always see that most of the values are very much closer to a number which you can call as a central value or average. And this property of concentration of the values around the central value, that is called as central tendency. You can pick any such variable, collect some data, you will observe that the values are closer to certain numbers. Say for example, I'm selecting the age of students who are pursuing say MSc degree, and I could have values like say 21, 23, 22, 21, 24, 25. Maybe I could have some extreme values, but if you look into most of the cases, I could say the
ಸರ್ ಏನು ಕೇಳ್ತಾ ಇಲ್ಲ ಸರ್, ಸ್ಟ್ರಕ್ ಆಗಿದೆ.
values are very much closer to the middle value. ಸರಿ ಇದೆ, ನೀವು ಕನೆಕ್ಟ್ ಆಗಬೇಕು. ಜಾಯಿನ್ ಥ್ರೂ ಇಂಟರ್ನೆಟ್ ಅಂತ ಏನೋ ಒಂದು ಆಪ್ಷನ್ ಇರುತ್ತೆ, ಕನೆಕ್ಟ್. How about now?
ಸರಿ ಸರ್ ಕೇಳ್ತಾ ಇದ್ದೆ.
Clear.
Okay. So whatever may be the type of variable you
ಸರ್ ರಿಪೀಟ್ ಮಾಡಿ ಸರ್ ಮೊದಲಿಂದ ಸೆಂಟ್ರಲ್ ಟೆಂಡೆನ್ಸಿ.
whatever the value of variable you observe in the nature, if you extract some data points on that, you will observe it is very much closer to a single value. So you collect any such data points, you can always come up with one value, which is called as central value in the layman language, or statisticians call it as average. And you can see that all other values are very much closer to that particular number. So this property of concentration of the values around that single number called as a central value or average is called as central tendency. And that number, which is the central value, that is called as measure of central tendency. And statisticians simply call that as average. And they commonly use the term average to indicate the arithmetic mean. So what we are doing here in this case is that we observed in the previous set of measures, they only try to, we are trying to capture specific values of x at various locations. So that's why they are called as measures of location, measures of position. And the major disadvantage of that is that they are based on only specific values of the observed data, and they are not solely based on all the observed data. Every piece of data, every numerical value captured, they are contributing, some information about the population. So they contribute some information about the population. So we have to capture that. So we are coming up with certain number of measures which are based on all those values. And such measures are arithmetic mean, geometric mean, as well as harmonic mean. And the most commonly used average is arithmetic mean, and statisticians simply call it as average. So average ಅಂತಂದ್ರೆ ಎಲ್ಲ measures of central tendency, all these 5 measures of central tendency are also called as average, and the default name for arithmetic mean is also average. So if you say or observe any book or any material suggesting that capture the value of average, in most of the case they are referring to the concept called as arithmetic mean. Why? The reason is it is very easy to understand, very easy to compute, and it is the most widely accepted and used average. The other two measures are again median and mode. So we'll take each of this and study what is happening in case of that, and we'll restrict ourselves to mean, median, and mode. I'll just give you the definition of these two measures, geometric and harmonic mean. I'll not look into the details of that. Now coming to this measure called as arithmetic mean. So we have certain variable, we have recording certain observations. So generally I say I have recorded some n values on these x, where the size of the sample is n. In that case, we define the arithmetic mean as the ratio of the sum of observations to number of observations. So it is basically the total of all your x values divided by n. And as said, we use the notation capital sigma to indicate the total of a particular characteristic. So here we are obtaining the total of characteristic x, and denominator is n, and we use the notation x and a short horizontal line, we call it as a bar, and we indicate arithmetic mean by x bar, or you can simply call it as am also. So when you're dealing with only the raw set of observations, you can compute arithmetic mean just by totaling all the values and dividing that by n number of observations. So this is the definition of arithmetic mean. So let us take an example. So I have some weight values here. If I want to compute the values of weight, 33.5, 48.6, 59.2, 21.8, 36, 43, 47. So extracted 7 observations on this variable called as weight. Then if I want to compute the value of AM, which is X bar, I need the total of all these values, and I have to divide that by the number of observations, which is 7. So take your calculator and just try and obtain the total of that. So add every value, like say 33.5 plus 48.6, that working need not be shown. You can just compute the total and substitute the total. 33.5 plus 48.6 plus 59.2 plus 21.8 plus 36 plus 43 plus 47. The total comes to 289.1. Now each of these values are in terms of kgs. Therefore, when you add a value 33.5 and 48.6 kg, the total or the sum is also in terms of kgs. And when you divide it by 7, the unit remains same. So one of the important property of this arithmetic mean is that it is using all the observation. So I could say the merit, it is based on all the values, and whatever the units you are using to measure, to capture that particular magnitude, the same unit are used to express the arithmetic. So that is one of the advantage. Now coming to the easiness of calculation. So it is just the sum divided by the number of observations. Now it works well with the data where you have less number of observations. Now if you, in the cases where you have n to be very large, like you have hundreds and thousands of observations, we could represent them in a frequency distribution, and we could obtain the mean of that frequency distribution. So we'll see how to calculate the mean for a discrete case as well as a continuous frequency distribution. Now, one of the major demerit of this arithmetic mean is that it is hard to interpret this, what exactly this 41.3 is representing. So we call that as the fulcrum value. The needle or the balance point of the balance is called as fulcrum. Now your arithmetic mean serves as the fulcrum value. Like say, if you could put all these values in a balance and hold the balance at exactly 41.3, the balance get balances. That is the interpretation. So that interpretation is hard to digest. So we say it is hard to understand it, but the calculation is very easy. Now coming to another major demerit, we cannot identify this arithmetic mean from any of the graphical techniques. And another case is that if you have the presence of extreme values in the data, that is values not properly corrected, or the values which are incorrectly recorded, or maybe because of some reason you have a data point which actually doesn't seem to fit in that, called as an extreme value. Now, if you say that instead of 47, you have recorded the number as 470, then the total just see changes to 712.1. And if you look into the mean of that, now it has become 107.28 kgs. So if you look into the observation now, this number is neither close to these set of values, and it is not close to this number. So though it is based on all the observation, whatever the average or mean I'm talking about, that is not a good value, and that happened only because of the presence of this. So that's why we use the measure of quantiles, and we try to chop out that particular extreme value. And whenever we try to chop the values, we often do that on the left extreme as well as on the right extreme, so that the tails of the distribution could be balanced. So if I completely remove this data point and this also, so I'm reducing one data point on each. Then if you look into the value of mean, so I'll have 48.6, 59.2, 21.8, 36, and 43. The mean comes to 29.8. Sorry, divided by 5 over. So which is 41.72, and that number is very much closer to the mean what we have got earlier. So that is how the percentiles are used in omitting the observations. But I just had only 7 observations, which is already a very less, statistically speaking. And of 7, if I'm removing 2 observations, now my n has just become 5. And using this mean, if you want to look into decision making as well as the generalization of that, that cannot be achieved because my size is very less. Now you can talk about the removing of the extreme values whenever you have larger set of data. And as far as possible, as said, it is the commonly used mean because only the mean gets fluctuated if at all there is a presence of extreme value. But when you are collecting the heights or weights of person, you hardly come across a number which is called as 470. So you'll come to know that it is by mistake it has been recorded as 470. You could just correct it by again capturing it so that now the corrections have made and you will get the correct value of mean. So I'm completely not denying that always there will be no presence of extreme values. There will be presence of extreme values. If at all there is an extreme value, see what you can do. If you have large number of observations, see whether you can omit them. If at all you have small number of observations, see what happens if you include them, and solely who are the decision maker. So this is about the computation of arithmetic mean for raw data. Now, when you look into the frequency data, frequency distribution, the first case what we'll talk is say discrete frequency distribution. What is discrete frequency distribution? Your variable x is taking several repetitive values which are discrete points and they are specific values within the range. Um, Let me say how the same definition, show you how the same definition is extended into this case. We have say the values recorded, like say 2, 3, 4, 6, 3, 2, 5, 1, 3, 4, 5. So I have this here. So let me take that as raw data, unordered data. So I have 4, 5, 9, and say 13 observations here. So when you compute the mean for this case, 4, 3, 7 plus 1, 13. So the total comes to 45 and the average arithmetic mean comes to 3.461. So some data is extracted. If you feel that it is raw, you can compute the values like the mean, the arithmetic mean using the same definition sigma x by f. Now, if you see that the same data is recorded for on a larger scale where you have 130 observations or 50 observations, 60 observations. So in that case, writing all and obtaining the sum becomes a tedious job. So what better we could do is we could present them in a frequency distribution so that each and every value is presented. And for the table, from the table, we try to obtain the mean for the values of x. Now, if I'm presenting this in a frequency distribution, so I have the range of the distribution as say 1 to 6. So I'll have 1, 2, 3, 4, 5, 6. And if you obtain the tally marks and obtain the frequency of 1 is 1, then I have 2 repeated 3 times, then I have 3 repeated 3 times, and then 4 2 times, 5 3 times, and then 6 1 time. So this is the frequency distribution. Now, if I want arithmetic mean, so the definition remains the same. It is always sum divided by the number of observations. Now, if you want to count how many observations are there, if you know each and every value like this, you can have a count and you could say it is 13, which is same as the count of the or sum of the frequencies here. Now, since frequency is representing how many times a particular value is observed in the raw data, if you obtain the total frequency, that is sigma f, that will be same as your n. So we use sigma f in place of the notation n. So for frequency case, we say that now the sum will be indicated by sigma f, and another notation for sigma f is capital N. Now coming to the value of the sum of the observations. So what we did is we added these values 2 plus 3 plus 4 plus 5 and so on. Now the sum could be also done by adding two values first and then the numbers 3 and then the numbers 4, 5 and so on. Now adding 2 3 times is same as multiplying 2 with 3. So 2 plus 2 is same as 2 into 3. Now for that I'll add 3 plus 3 plus 3, which is nothing but 3 into 3, plus 4 which is nothing but 4 into 2. So logically if I'm adding the values of x, it is same as doing the product f into x. That is, every value of x is multiplied by itself, and then we are looking into the sum of all those sums. So we are talking about the concept of sigma fx. So multiply every value of f with its x, 1 into 1, 3 into 2, 3 into 3, 4 into 2, 5 into 3, 6 into 1, and obtain the total of that. You will observe it to be 45 and 13. So the numerator in the formula of mean is replaced by x bar is equal to sigma fx, and we take this as the formula to compute arithmetic mean whenever we are talking about a discrete frequency distribution. Okay, join back again.